Hello everyone, welcome to webinar talking about upper reservoir settlement, calibration, and the prediction of a pump storage. I'm Jim Shore, presenting this project after I have worked on as the China ITASCA. I will present to you some of the key approaches we have used during the project. So for the first slide, I showed the overview of the project. The project upper reservoir settlement calibration and prediction of a pump storage is used in the power generation, and the objective is calibrated models to predict a maximum settlement at final water level and analyze 20-year creep behavior and validate with the monitoring data. And the parameter calibration of the modified clay model for short-term and convert the plastic hardening soil parameters to softer soil model for long-term. Recommend back compaction improvements as the inner corners. The software we used is the Flag 2D. There is the introduction of myself. I'm from ITASCA China office. I got 3 degrees from the Wuhan University in China and major in water resources and hydropower engineering. So now let's talk about the project background. On April 18, 2024, during initial reservoir operation, the client observed the leakage and abnormal deformation of the geomembrane around intake area of the upper reservoir due to the localized compaction deficiencies. This led to a series of inspections and interventions. The client needs to know the maximum settlement value after water storage to the normal water level and the long-term settlement in the future. Let's begin with the overview of the project. The installed capacity of the power station is the 344 megawatts, and the storage capacity is the 3.16 million cubic meters. The project comprises an upper reservoir, a headrace tunnel, and powerhouse, and an access tunnel, terrace tunnel, and the lower reservoir. And this is the upper reservoir, and this one is the intake of the upper reservoir. And the key objective is to estimate the settlement deformation of the backfill soil around the concrete structure of the intake, and predict a maximum settlement value after water storage to the final water level. Analyze the 20-year creep behavior. We also validate predictions against the field monitoring value. Finally, we adjust the client to optimize compaction in the high-risk zones. There are the challenges we have encountered in this project. First one, the calibration of the short-term MCC and the long-term soft soil creep model was evaluated through the field displacement monitoring and dive inspections, serving to optimize the engineering implementation and enhance the structural safety. And the key challenges is the constitutive model calibration. The difficulty in calibrating MCC model parameters with a limited initial impounding data, and the significant parameter sensitive at the soil-concrete interfaces. And the second one is the long-term behavior conversion. Transfer the hardening soil model parameters to the softer soil creep formulation and calibrate the creep index without direct creep measurement at intake zone. And as you can see, the two factors of the MCC model are the slope of the normal consolidation line and the slope of the elastic swelling line. And then we need to convert the plastic harmony model to the softer soil model for a long-term analysis. The ITASCA's role is deployment of the FLAC 2D's advanced modeling capabilities for settlement prediction and executing the parameter calibration and implementing long-term behavior modeling. And it is clearly a scope of the work. First one is the short-term calibration, and the second one the long-term prediction, and the last one is the field validation. Okay, I will talk about the detail of this. And we can get the details clearly from this photo and pictures. And this is the intake. This is the concrete structure, and there are the backfill clay. And in this picture, you can see this is the initial design. This is the concrete structure of the intake, and this is the backfill clay, and the red line is the geomembrane. And after the water storage, differential settlement occurred around the intake of the upper reservoir, and this caused the abnormal deformation of the geomembrane. And this currently out of the water intake photos of the imposed failure of the geomembrane are demonstrated. Here we present a plan view of the upper reservoir intake and the geological profile of Section A. Detailed indication and the plan view of the upper intake, along with the geological profile of the Section A, are crucial for understanding the soil parameters. And there are three layers: clay layer and clay with gravels and a rock bed. According to the approved upper reservoir geotechnical parameters of clay formation report, we have summarized the soil parameters here. And this is the settlement cloned map, and the settlement around the concrete structure line of intake is generally 25 centimeters to 50 centimeters, and the maximum settlement is about 60 centimeters near the side of the concrete structure. And the settlement diminishes with increasing the distance from the structure, and the settlement on the left side of intake is generally greater than that on the right side. This accident need to be quickly fixed by the field team. At the same time, we need to predict how much extra settlement will be if final reservoir level is reached. And from the settlement cloud map, the damage location of the geomembrane corresponds to the location with a significant settlement. It observes that the settlement severe subsidence is basically concentrated in the inner corners. This speculated that it's difficult to fully crash the part during lowering as shown in this figure, which directly led to a failure of the backfill soil to reach the required design parameter. From the clone map, it can also see that except for the large settlement problem around the intake area, all other settlement relatively limited, indicating that rest of the soil is easy to compact and reach the design parameters, resulting in a small settlement. Two-dimensional numerical model is figured to match the intake profile of section A, as shown in this figure. The numerical model incorporates two soil layers and the bedrock. An interface is modeled between the backfill material and the intake concrete structure. And for the short-term behavior, we have conducted a parameter calibration of the modified chem-clay model. Two main factors were considered in the back analysis: the slope of normal consolidation line lambda and the slope of the elastic swelling line kappa. And these values are obtained through the back analysis of the MCC model. Then we have to analyze the settlement at the three different stages. The first stage is the result of the impounding to the 203 meters for the first time. and stage 2 is the reservoir empty, and the last stage is re-impounding to 207.8 meters. And this figure shows the settlement results of impounding to 203 meters for the first time. In the second stage is the reservoir emptying. The maximum measured settlement is the 0.376 meters, and the average measurement is about 0.23 meters with 30 meters of the central axis. In comparison, the mean value of the MCC model is about 0.329 meters with the 50 meters of the central axis, and the interface parameters shear stiffness and normal stiffness are 1.5 MPa. And the last stage upon impounding to its normal water level of the 207.8 meters. The figure shown illustrates the predicted increment settlement. The mean increment settlement value of the final level at the 207.8 meters is 0.126 meters, with a maximum increment settlement of about 0.145 meters. And in conclusion, with calibrated soil parameters of modified chem-clay model, initial settlement after water emptying is estimated at the 0.376 meters, with an additional 0.145 meters expected as the water level rises to 207.8 meters. And after 10 days of impounding to the normal water level, the diver made an underwater inspection of the intake and average settlement before and after impounding is the 17.9 centimeters, and the settlement increment near the intake structure is about 14.5 centimeters, which is similar to the monitoring average. And for the long-term analysis, we need to convert the hardening soil parameters to the soft soil model properties. We have used the design parameters as a benchmark and refer to the design reports for the backfilled material properties. Because the embankment has been built before the intake and has 1 year monitoring grip data, through the triaxial tests, we have calibrated the backfill material properties and convert them to the soft soil model properties. The confining pressure range of the test is 15 kPa to 300 kPa, corresponding to the maximum annular pressure of the dam body, about 200 kPa. The triaxial test considers the loading and unloading conditions and checks the loading and unloading the soil modulus. Then, comparing the results of the modified chemical model and the soft soil model, we find that short-term settlement using the two methods are generally similar, with the MCC model showing slightly higher settlement in terms of the domain and the peak value, and the results of the MCC model is more conservative for the design. And the creep behavior is calibrated from the settlement curve on the embankment. This figure shows a plan view of the monitoring layout of the upper reservoir, where a number of the displacement monitoring points, the ESU1, ESU3, ESU5, and the pore pressure monitoring sections, the U1 to U5 and U7 and U8 have been placed. And most of these monitoring instruments are installed from the 2019 to the 2020. And this figure depicts the deformation curve monitoring as the ESU1. And the pore pressure is typically small and treated as the zero pore pressure based on the feedback. Following the July 2023, all displacement monitoring points on the northern section stabilized, with the maximum deformation of about 48 millimeters. So the grip behavior is calibrated from the settlement curve on the embankment, and you can see these two curves are the maximum the monitoring data, and this line is the numerical data. And so a grip index of the 0.001 is obtained from the grip behavior calibration. And then, considering the current material properties, the final settlement is predicted to be about 0.15 meters over the next 20 years. And the result you can see in this figure. So in the end, this study provides a comprehensive analysis of the settlement behavior of an upper reservoir. And in terms of the short-term failure analysis and the interface parameter has more predominant influence on the excessive movement. And the calibrated MCC model and the soft soil model offer value insights into both short-term and long-term behavior, which are crucial for the ongoing management and maintenance of the reservoir. Okay, thank you for your attention.